an intense lecture today. It's going to be trying to do complex analysis that we need for probability in just one day. And so if it doesn't work, if it takes 2 days, that's fine. I really don't want to go into 3 days. But what I want to do is I want to give you some sense of why all the stuff we're doing works and what we need to do to make it all vigorous. So you're going to see some of the stuff from Calc 3 again, and you're going to see now why we care about some of those theorems. You're also going to get a chance to see what we need to do to make analysis rigorous and get a sense of what would you do in a complex analysis class. If you're thinking of math grad school, this is one of the big classes that you need to know. All right, so complex analysis. And again, I am deliberately not telling you what we're doing over the last few days, so it's a little bit of a surprise. I don't want you to be spending too much time preparing. I want you to just sit back and enjoy. I am not going to be putting stuff on complex analysis on the exams. Why am I still doing this? It's important material, and it's a great way to review a lot of what we've done, both in this class and in other classes. All right, so complex analysis. So x and y are real. We often write x, y are elements of R. Then z equals x plus iy is a complex number. Here I is, or I am, the square root of -1. So I squared is -1. We also have the polar representation. We can write z as r e to the I theta, 0 less than or equal to r less than infinity, 0 less than or equal to theta less than 2 pi. Of course, I could have theta go beyond 2 pi, and it's not going to really change. We have the following formula, Euler-Coates, I believe. I'll just do it Euler. E to the I theta is cosine theta plus I sine theta. Sometimes in high school, they use the cis theta notation. Anybody ever see cis? OK, so at least one person saw it, so it's almost dead, but not quite. All right, how would you prove some of this stuff? So let's go back to Taylor series. So e to the u is 1 plus u squared over 2 factorial plus u cubed over 3 factorial plus dot 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 is the sum, n goes from 0 to infinity, of u to the n divided by n factorial. All right, so that's the series expansion for e to the u. You can calculate the series expansion for cosine of u. It's 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus dot dot dot. You can do the expansion for sine of u. It's u minus u cubed over 3 factorial plus u to the 5th over 5 factorial minus dot dot dot. And the way we're doing these Taylor series is, f of x is the sum of the nth derivative at 0, x to the n over n factorial. N goes from 0 to infinity. It's not always clear when the Taylor series will converge. And when does the Taylor series converge and equal the original function? We've talked at times about how there are very bad functions. The bad function is e to the minus 1 over x squared if x does not equal 0, and 0 if x equals 0. All of the Taylor coefficients of this function at 0 are 0, but the function is not identically 0. So the only place where the Taylor series agrees with the original function is at the origin. And really, this is not that impressive, because you force it to agree. You force it to start off f of 0 plus everything else is multiplied by at least x. So when you put in x equals 0, they have to agree. This is not impressive to have agreement at x equals 0. You force agreement at x equals 0. What you really want is you want agreement in some neighborhood. If you think of what we're doing in complex analysis, we have these assumptions about moment-generating functions. We want the moment-generating function to converge in a small interval containing the origin. It's coming in some sense from something like this, from wanting the Taylor series to be nice. When you prove the formulas for sines and cosines, well, if you keep taking the derivatives of sine and cosine, you get this beautiful alternating pattern. The derivative of sine is cosine. The derivative of cosine is negative sine. If you do it 4 times, you come back to where you started. And that's why you get these coefficients. 1, 0, minus 1, 0, 1, 0, et cetera, et cetera, et cetera. And then it turns out if you just replace u with I times x, you'll then get e to the I x is cosine x plus I sine x. So you just go through the Taylor series, and you get e to the I, am I doing theta? I'm doing theta, I guess. Theta is cosine theta plus I sine theta from the Taylor series. Okay, so that's not a bad start. All right, and this is a beautiful formula that links sines and cosines and the exponential function. This is why these functions have a lot in common. If you think back to the angle addition formulas, you know, we have, let's do cosine of x plus y is cosine x cosine y minus sine of x sine of y. E to the x plus y is e to the x e to the y. These are all related. You get from one to the other. And the way you prove these things is if you take e to the I theta plus phi, this is e to the I theta, e to the I phi. Over here, this is cosine theta plus phi plus I sine theta plus phi. Whereas on this side, it's cosine theta plus I sine theta times cosine phi plus I sine phi. And so if you now multiply everything out, these two sides have to be equal. And so the cosine of theta plus phi, that has to be the real part here. It's going to be cosine theta cosine phi minus sine theta sine phi. So if you have two complex numbers, the only way they can be equal is if their real parts are equal and their imaginary parts are equal. You can deduce all of trigonometry from knowing this relation. Now again, we need the fact that this is true. If this were not true, this would be a horrible notation. Right? When you think of e to the x plus y, you think of e to the x times e to the y. We've talked earlier about how you have to prove this using series expansions. E to the x plus y is the sum, n goes from 0 to infinity, of x plus y to the n over n factorial. E to the x was the sum, L goes from 0 to infinity, of x to the L over L factorial. E to the y was the sum, m goes from 0 to infinity, of y to the m over m factorial. And you have to show that this series is the product of this series times this series. So you have to rearrange the terms in the sum. We use the binomial theorem to prove that. All right, this is a really fast introduction to complex analysis. Some of this stuff we've already seen before, and so we're reviewing it. If you also think back to your old calculus classes, how did you get the formulas for e to the x? How did you get those derivatives and all that stuff? Well, if you define e to the x as this infinite Taylor series, you want to basically differentiate term by term. And if you can differentiate term by term, you will then get the formula for the derivative of e to the x is e to the x. All right, so this was a really fast introduction to sum of complex numbers. So we've got the real and the imaginary parts. They're equal if and only if the two real parts are the same and the two imaginary parts are the same. The function e to the I theta is cosine theta plus I sine theta. The next thing we want to do is we want to build up functions of a complex variable and differentiate. So when I teach Calc 3, I don't know if I can still do this, but in the past when I taught it, I always had at least one kid in preschool. And so what I did is, it's kind of like violating child labor laws, but the teachers didn't really mind. I had Kayla and Cam's class make scribbles for my students. And each student got a personalized scribble. I think some of you still have them. So everybody would get a picture like this. Anybody here see the Karate Kid movies? Oh dear God, this few people have seen the Karate Kid movies? Okay, the second one where he goes to Okinawa and they learn the secret of Miyagi karate. Okay, this is the secret of multivariable calculus or complex analysis. If you understand this picture, you understand everything. Okay, let's go back to one dimension. I want to calculate the derivative at a point. How many ways can I approach this point? Two, essentially. I can go this way, I can go this way. Life is not that exciting. I walk this way, I walk this way. Oh, good, the camera tracks me, good. Okay, there's not that much you can do. So if I tell you a function is differentiable, what does it mean for a function of one real variable to be differentiable? It means the limit as h goes to 0 of f of x plus h minus f of x divided by h exists, and we'll call that f prime of x. Well, there's only two limits that we're computing. One of the big misperceptions in Calc 3 is that a function is differentiable if it's differentiable with respect to x and differentiable with respect to y. This is often glossed over in Calc 3 classes. It's not enough for the partial derivatives to exist. If the partial derivatives exist and are continuous, then you're okay. But there are functions where the derivatives, the partial derivatives exist, but the function is not differentiable. What should it mean to be differentiable? It should mean no matter what path you take, the limit exists and it's the same limit. This is why multivariable calculus or complex analysis is either a lot harder or a lot easier, depending on your point of view. It means that if you take this path, you must get the same answer as if you take that path or this path. Which path would you rather take? Horizontal, vertical, or Taylor-Cram scribble? Can anybody even parametrize and tell me what the Taylor scribble would be? I don't want to take a derivative. I don't want to take a limit along that path. I want to flow down the axes. What's wonderful is that if the limit exists, it doesn't matter which path you take, they all give you the same answer. So if you want to compute something, how would you compute it? X-axis, y-axis. And that's going to be extremely important later. Okay? If you want, thinking back to Calc 3, think of your directional derivative. There are certain definitions for it, and then you have a really nice formula that you can use. The whole point is to get to a nice formula. We want to get the paths coming in just from the x to the y. But the difference between Calc 3 or complex analysis and just Calc 1 is that now if I tell you a function is differentiable, I am telling you a lot. I'm telling you that no matter what limit you take, you have to get the same answer. Because of that, it's much harder to be complex differentiable than to be real differentiable. And there will be plenty of functions that are complex differentiable that are real differentiable. In fact, they'll all be. But there are functions that are real differentiable that are not complex differentiable. And that's why complex analysis is so much nicer. The bad functions are excluded. If I say I'm dealing with a differentiable function, all of the difficulties, all the problematic functions are just not even allowed into the discussion. And that's why the subject becomes so much nicer and so much cleaner. I have a slight dispute with some of my colleagues. As this is being recorded, I will have to be very careful. I think I talked about Erdős. You don't need to believe in God, but there is the book. This is the book where God has the proofs, right? You do not necessarily have to believe in God, but for me, I believe that when I die and my life is being weighed, if my Calc 3 students have not seen Green's theorem, I will be found deficient and lacking, and I will be penalized in the afterlife if there is one. So I make sure my Calc 3 students have seen Green's theorem. If you're a math major, you should see Green's theorem. If you're a stats major, well, yeah, we've expanded this class and now have 2 designations. You may go through life not seeing Green's theorem if you're a stats major. It's useful to see, but there is a few slight differences in these courses. How many people have seen Green's theorem? Okay, so I will quickly state what Green's theorem is. If you haven't seen Green's theorem, if you're going to be a math major, this is something you need to learn. I will put a link to a lecture on this. It is a phenomenally important result. It converts 2-dimensional integrals to 1-dimensional integrals, or 1-dimensional integrals to 2-dimensional integrals, depending on which way you want to go. Why do you want to do this? Frequently, one of the integrals is easier than the other. And the whole point is to convert to something that can be calculated well. It turns out if a function is complex differentiable, when you do Green's theorem, you're dealing with special functions whose curl is 0. So let me quickly state Green's theorem because we'll need it later. This is sometimes called Stokes' theorem in a plane. So if I want to integrate p dx plus q dy over some curve gamma in the plane, I'm not going to be too specific. I have some nice closed curve, and I have some nice region that it encloses. This is the same as the integral over the region we'll call the region, because I have no originality, dq dx minus dp dy. So this is Green's theorem. This line integral, this integral along the curve, is the same as this. The way you would do this is you would have some function f of xy would be p of xy, q of xy. You would have some curve c of t would be x of t, y of t. I'll have my function, here's my c of t, here's my function pq. I'll basically be taking a dot product. And that's what this is going to be. That's how you do a line integral. This is a very fast review of things you should have seen in Calc 3. One of the whole purposes of math is to build on what you've seen. You spend a lot of time in Calc 3 learning material. It's kind of nice to know that this material was done for a reason. It's so that, well, we've got 12 weeks. We've got to put something in at the end of the semester. Green's theorem is important. So, again, if you haven't seen it, do not worry. This class is supposed to try to function at several levels of reviewing a lot of the stuff you've seen. Why is this nice? If you could choose any functions q and p, what would you like dq dx minus dp dy to be? No. Which constant? 0. If you had a choice. Because if you choose the constant to be 1, then the integral over the region is the area of the region. You have to compute the area of the region. That could be hard. If you had your choice, if the world were nice, you would have functions p and q such that dq dx minus dp dy is 0. It turns out if your complex function is complex differentiable, the associated integrals we need to look at turn out to have this quantity equal to 0, and all the integrals turn out to be 0. What does it mean for an integral to be 0? Well, it means if I split this up in half, then the integral over the bottom is the integral over the top. And it's going to allow me to calculate integrals very easily. So the reason complex analysis works so nicely is most integrals are 0. And since most integrals are 0, then the integral over one part is the integral of another part. You can transform things very quickly and very nicely. OK. Any questions so far? So a lot of it is just motivation. We're going to see Green's theorem. We're going to see why we care about Green's theorem. This is notation on complex functions and numbers. So now let's go to the definition. F is complex differentiable at z if the limit as h goes to 0 of f of z plus h minus f of z over h exists and equals f prime of z. And we denote. Does this look familiar? Yeah. This is the same definition of differentiation as we've seen before. The only difference now is how h is allowed to vary. In Calc 1, these are my paths. Paths for h. In Calc 3 or complex, remember, it's the scribble paths. And we need all those scribble paths to exist and have the same limit. OK? So let's do some examples. What's the easiest function to look at? It'll be so easy I won't even let us do it. 0. All right. Slightly easier than 0, but essentially as easy. 1 or any constant. So if I take f of z to be a constant, well, I get c minus c divided by h. Doesn't matter what that is at all. It's clearly going to be 0. All right. We could take f of z equals z, or f of z equals z squared. Let's do both of them and just really build up some intuition. So if we take f of z equals z, so example 1, f of z equals z, we get the limit as h tends to 0 of z plus h minus z divided by h. Well, if you look at the numerator, the z's cancel, and h divided by h is 1. The limit as h goes to 0 of 1 is just 1. All right, not so bad. Example 2, f of z is z squared. limit as h goes to 0 of z plus h squared minus z squared over h. This is the limit as h goes to 0. When I square, I'm going to get a z squared, which cancels with the z squared. And I'm going to get 2zh plus h squared divided by h. Now, whenever you do these calculations, remember, when I write h goes to 0, there's one number that h can never be. What number is h never?
0.
H is never 0. The whole point of calculus is you can't divide by 0, but you can divide by things that are very close to 0. And then you look at what happens in the limit. Calculus is all about limits. So here, I can divide by h because h is not 0. This is the same as the limit as h goes to 0 of 2z plus h. All right, well, as h goes to 0, what does 2z plus h go to? 2z. So far, you should be thinking, big deal. This is essentially just reproducing everything you've done in Calc 1. All right, let's take a more interesting function. I want a function that's still nice, but easy enough that I can do it on the board with very little sleep, because I don't think I got in until today. Let's take f of z is the complex conjugate of z. So this is f of z is x minus iy when z equals x plus iy. So the complex conjugate just replaces I with minus I. If you want to plot where you are in the complex plane, if you're over here, then the complex conjugate comes down there. It's flipping you through the x-axis. Is this a continuous map? Yeah. You know, if I start off, if I move over here a little bit, I just move over here a little bit. This is a nice map. It's continuous. It's differentiable as a function of x and y. So f is real differentiable. Do you think it's complex differentiable? Based on the fact that I'm telling you not all functions that are real differentiable are complex differentiable, and I'm talking about the need to do a more interesting example, this should hopefully have you primed to believing that this function is not complex differentiable. Notice that in what we were doing over here, I'll move so the camera gets, over here, did I really worry about all the Kamm-Kähler paths? No, I was able to just do the calculation. I could take the limits without any trouble. If I think the function is not complex differentiable, what that means is there should be two paths that return a different answer. Or there should be at least one path where the limit doesn't exist. So this is similar to one of the questions on the midterm which gave people problems, where I asked you, consider, does the following hold for all probability distributions? If you can find one distribution where it doesn't hold, you're done. So over here, if we want to prove something is not complex differentiable, it's not necessary to consider every possible path. Let's just try to find two paths that give a different answer. What would you suggest as two paths to try? What would you try for your two paths? X and y axis. Why? Or x and y. Why those two? They're easy, right? Try the easy things first. If the easy things don't work, then try something more complicated. But if the easy things work, there's no need to consider more painful algebra. So let's look at the limit as h goes to 0 of f of z plus h minus f of z over h. This is the limit as h goes to 0 of z plus h. So I take the complex conjugate of that, I subtract the complex conjugate of z, and I divide by h. The complex conjugate of a sum is the sum of the complex conjugates. All I do is I replace I with minus I. So if I have 2 plus 3i plus 4 minus 8i, and I take the complex conjugate of that, that's the same as 6 minus 5i complex conjugate. And here you'd get 2 minus 3i plus 4 plus 8i, and here you would get 6 plus 5i. The complex conjugate of a sum is the sum of the complex conjugates. So the complex conjugate of z plus h minus the complex conjugate of z, what does that equal? The complex conjugate of h. So what we get on up top is the expression up top is just the limit as h goes to 0, the complex conjugate of h over h. So now we want to explore this along two paths. So path 1, h is real. Well, if h is real, then what's the complex conjugate of h? H. So then the limit as h goes to 0, h is real, of h bar over h is just 1. All right, let's look at path 2. H is pure imaginary. So we're going to write h as maybe I times k, where k is real. So h bar is going to be minus I times k. So the limit as h goes to 0, h is imaginary, of h bar divided by h is the same as the limit as k goes to 0 of minus ik over ik. And what does that limit equal? -1. And so these two limits are not equal. So we have an example of a function that is real differentiable, but is not complex differentiable. What's wonderful about that, that means, great, if I want to consider complex differentiable functions, I don't need to consider this one. It's not in our realm of discussion. Yes?
Are you allowed to have limits as they approach I?
I'm sorry?
Are you allowed to have limits?
Yeah, you can have limits approaching any point. I'm just having limits approach 0 because I'm taking the derivative. If I want to take the derivative at the point 5, I would replace z with 5. If I wanted to limit at the point 5 plus 3i, I would have 5 plus 3i here.
Sorry, just to clarify.
Yep.
In the first path, when the complex conjugate of h is h, that's just because h is real.
That's because h is real. Exactly. Exactly. And so if we take h to be real, this limit is 1. If we take h to be pure imaginary, the limit is -1. Okay? Any questions about this? So not all functions are complex differentiable, that are real differentiable. So there is a significant difference between the two. All right. So the question is, why do we care about all this? So I'm deliberately going to leave Green's theorem up on the board. I'm going to erase this example. I'll erase the other example. I'll erase the definition of complex differentiable. Well, maybe I should have kept that. All right. So there's a beautiful set of equations, the Cauchy-Riemann equations. When you take a first course in complex analysis, you basically spend your entire semester alternating between results of Cauchy and results of Riemann. These are the two big guns who proved an incredible number of things. I always forget which way the Cauchy-Riemann equations go because I always rederive them on the spot. So it's du dx equals dv dy, and du dy equals negative dv dx. So here, f of z is u of xy plus iv of xy. So these hold if and only if f is complex differentiable. We will be getting enormous dividends from all of this. So remember earlier in the semester I gave you two probability distributions that had the same moments but were not the same? We're actually going to calculate their moments. And we will actually calculate that all of their moments are the same, but not all their generalized moments. And we will get a sense of why the central limit theorem fails in certain cases and what we need to make it rigorous. So the big picture that we're aiming for is we will actually look at those two distributions that cause so much trouble. In doing so, we're going to meet a new distribution, the log normal distribution. So another reason why I want to do this is a way to introduce you to yet another probability distribution that surfaces in many problems. The more things you have on your radar screen, the better chance you have of successfully modeling things. I think somebody chose to look at the log normal distribution in their write-up of an interesting paper to look at. And so again, lots of good stuff that's going to be coming. So the question is, why are these true? So why true? So let's assume f is complex differentiable. All right, so what does it mean for f to be complex differentiable? It means that if we take the derivative along any path, we get the same answer. So what are our two favorite paths? Along the x-axis and along the y-axis. So f prime of z is the limit as h goes to 0 of f of z plus h minus f of z over h. And I can do the limit as h goes to 0, h is real, f of x plus iy plus h minus f of x plus iy divided by h. And this is the same. Make sure you leave a little bit of room. Limit as h, all right, is ik. K is real. K goes to 0 of f of x plus iy plus ik minus f of x plus iy over ik. So I'm just writing down the definition of the derivative, and I'm doing two different paths. In the first path, h goes to 0 through reals. In the second, h equals ik, and k is real. So I'm going along the imaginary axis. If you look at this, this is the same as the partial derivative of f with respect to what variable? X. This is the same as df dx, which is going to be du dx plus I dv dx. This is where it's really nice to have a big blackboard. What about the second one? What derivative is this? Yes, why? Because of the i's. This is a great way for me to review one of our favorite techniques, grouping. I've got x plus iy plus ik. Well, let me just put the parentheses in like that. And so really, I've got x fixed. If I consider this just as a function of y, here is y plus k, here is y divided by k. But I have this extra I now in the denominator. So this is equal to 1 over I, partial of f, partial of y, which is now going to be 1 over I, partial of f with respect to y, is du dy minus 1 over I, from this, let me do this carefully, plus 1 over y dv dy. Oh, sorry. And then the I cancels there, sorry, right? Because f is equal to u plus iv. And so when I take the derivative of iv with respect to y, I get I dv dy. The I cancels. Well, 1 over I, if I multiply by I over I, this is minus I. So this becomes the same as minus I. The only way two things can be equal is if the real parts are the same and if the imaginary parts are the same. So if the real and the imaginary parts are the same, what has to be true? Well, dv dy, the real part here, has to be du dx. Yes, good. And dv dx has to be negative du dy. dv dx, good. And there's the Cauchy-Riemann equations. Okay, so the Cauchy-Riemann equations follow immediately from something being complex differentiable. The question is, who cares? Right? The reason we care so much is because of Green's theorem. Right? Took almost the entire semester, but I finally remembered to leave something important on the board. Okay? Why do we care? If dq dx minus dp dy equals 0, then things are going to be very nice. Yes?
Because there's an if and only if there, does that mean that
If the Cauchy-Riemann equations hold, the function is complex differentiable.
but then does it also mean that like you only have to try the path of the x-axis and of the reals and the
I don't want to go into, unfortunately, too much on the complex analysis right now. There is an if and only if, and there are questions about, if you know limits exist, which paths are sufficient to check. I want to try to avoid as much as possible these technicalities in the class right now. So what all we need is that if the function is complex differentiable, then the Cauchy-Riemann equations hold. But instinctively, I can't help but write the if and only if. So now, when we're looking at something like this, what we're going to be doing later, probably tomorrow, is let's say I have some integral along a closed curve. And I've got my complex differentiable function f. Okay? And I want to consider an integral. And so I want to consider the integral of f dz over my curve gamma. The circle over here means it's a closed curve. It comes back to where it starts. Well, this is the same as the integral over gamma of u plus iv, and dz is dx plus I dy.
What are the circles and integrals?
Well, I just said that. The circle means it's a closed curve. It means it comes back to where it started. So I have some closed curve. I return to where I began. Why is dz equal to dx plus I dy? Well, z equals x plus iy. In a really rigorous class, you would go through this very carefully. You would talk about line integrals. You would talk about parametrizing your paths. Hopefully, you've seen this in 150, 151. If not, don't worry about it. I'm trying to motivate. When you see something like this, what's your instinct to do? What do you want to do? So again, even if you don't care about all the complex analysis and the proof of the central limit theorem, there's a lot of good math skills we can get just by looking at this problem. How should we approach this algebra? What's your instinct? Expand. And when you expand, how do you want to group things? Group the reals together and group the imaginaries together. This is one of the few places where you are allowed to segregate. All right? You don't want the reals and the imaginaries mixing up with each other. So if I group them, I'm going to get the integral over gamma of u minus v. I'm sorry. It's u dx minus v dy. And now I get I times the integral of v dx plus u dy. Now what theorem should we use? Green's theorem, right? There's a reason it's still on the board. In here, this is the case of Green's theorem where p is equal to u and q is equal to negative v. So now we use Green. How many times do we have to use Green's theorem? Twice. And so the first one is going to become the integral over the region. So we get negative dq dx minus dp dy. Let's see, goes here, dx dy, plus I times the integral over the region. Now we take dq dx, so du dx, minus dp dy, dx dy. Well, by the Cauchy-Riemann equations, what du dx and dv dy, they're equal, right? So what does this integral equal? 0. And similarly, when you use the Cauchy-Riemann equations, this is 0. Complex analysis, in some sense, is the science of doing the easiest possible integrals. I want to integrate 0 over a region. Done. Okay? Now, of course, it's not going to be useful if we're just integrating 0. This is very similar to combinatorics. How did we do all these great combinatorial results? We told a story. And we told a story by looking at an expression two different ways. And by looking at the expression two different ways, we could get the answer to what we wanted from another related problem. So, one of the earliest stories we told was the following. N plus 1 choose k plus 1 was n choose k, and I'll write the 1 choose 1 plus n choose k plus 1, 1 choose 0. If I have n plus 1 people, and I want to choose k plus 1 people, and I have n wonderful people from Williams and one from Amherst, there's two ways of doing it. I take the person from Amherst, and then I have to have k minus people from Williams. Or I don't take anybody from Amherst, much better case, and I have k plus 1 Williams students. We told a story. And by telling a story, we can relate the two. We also told stories for the sum of n choose k, n choose n minus k was 2n choose n. We told a story. And by telling a story, we saw the two sides were equal. This is what we're going to be doing in complex analysis. When we have this integral is equal to 0, it's only useful if we can then write this integral as another way, as another thing that we need. Okay? So we have done an enormous amount of complex analysis today. We've still got about 6 minutes left, so we can either do a little bit more of complex analysis. We're not going to be able to finish everything today, or we can just do a random probability problem. My vote is probably to do a random probability problem right now, shift gears a little bit, and then finish the complex, give you a little bit of time to digest this. All right. But again, the whole point of this complex, this is where an hour 20, an hour 15-minute class would have been so much nicer. We're doing most of maybe a month of complex analysis in a day and a half. It is a lot to do, it's a lot to take in, it's a lot to absorb. A lot of this is in the books. I want you to see some of the advanced material as to why everything holds. We've done a lot of applications. I want to mix the applications with theory. I want you to get a sense of what we need to do to make everything rigorous. I also want you to see how the math you do in your other classes fits in. Why did we spend so much time proving Green's theorem? Hopefully time was spent in your classes proving Green's theorem. There's always a choice, there's always a pain in terms of what do you want to cover in a class or not. All right, so let's do a baseball problem. I will assume a series is 3 games. All are independent. Assume win a game with probability p. You win a series if you win more games than lose. And can anybody tell me an important contribution of the former commissioner, Bud Selig, to baseball that is now extremely relevant? What, cannot tie. I believe I've already commented that we do not have enough time in this semester to go into great detail as to why a tie in a baseball would be a catastrophe, although it is okay in my daughter's league. All right. I want to know what's the probability we win a series. So here's my question. For what p do you have the same chance of winning the first game as winning the series? Any thoughts?
0 or 1.
Okay. So you got that damn fast. Okay. Why 0?
If you lose the first, guaranteed, and the others, you're going to lose the series.
Good. So if you never win a game, you are not going to win the series. So your chance of winning the series is 0. Your chance of winning the first game is 0. Look for extreme cases. Check extreme cases. All right, what about 1? If you always win a game, then your probability of winning the series is 100%. Yes? 1/2. Why 1/2?
You have half chance winning the game and half chance winning the series.
So here's the interesting question. Is there a third? Could there be another p, and if so, is it p equals 1/2? So if you have a 50% chance of winning a game, do you have a 50% chance of winning the series? Why? By symmetry, but we need something special. There's something special about one of the numbers here.
More games.
3 games.
I'm sorry?
3 games because it takes 2.
Okay. Because it's odd. It's a 3-game series. If it was a 4-game series, would you have a 50% chance of winning the series? No. Because 3 is odd, there will be a series winner. So 3 odd implies series winner, implies p equals 1/2 works. So if p equals 1/2, you have a 50% chance of winning the first game. You have a 50% chance of winning the series.
It would be a really bad series if it was even.
I'm sorry?
It would be a really badly designed series if it was even.
It would be a very badly designed series if it was even, yes. And looking at how some things in sports are designed, my favorite is, how many of you are familiar with the Olympic badminton scandal, women's badminton a few years ago? One of the Chinese national teams realized it was in their best interest to deliberately lose one of their matches so that they would not be seeded against the other Chinese team. And once they did this, then the South Koreans said, oh yeah, well, we can lose too. And you then had 4 teams deliberately throwing their matches. You had the British fans furious as they're watching. I mean, they weren't even being subtle. They were deliberately missing. They were deliberately hitting into the net. And all 4 teams were disqualified, which I thought was completely unfair. They realized that the way the rules were set up, and they had warned people ahead of time that the rules were done foolishly. But they said it's in our best interest not to play our hardest. So there are sometimes poorly designed things. Baseball, thanks to Bud Selig, will not be in that category. Okay? Is there any other p that works? We got 3 of them really fast. So what's the probability we win the first game? Probability win first game. What does that equal to? P. And the probability we win series? What does that equal to? It's just Professor Gowdy. You'll get used to it. Okay, so p squared, and what is q?
1 minus
Okay,
times 2.
not times 2. No, what do we have to multiply this by?
Whatever it was for
It's either 3 choose 2, we have to choose 2 of the 3 games to be won, or 3 choose 1, we have to choose 1 of the games to be lost. So again, this is one of the reasons I like this problem. I can use this to review a lot of the stuff. We have a binomial process. I have to choose 2 of the 3 games to be wins. For the last one, instead of writing p cubed, I'm going to be overly pedantic and write 3 choose 3. So we want these to be equal. So we want p to equal 3p squared 1 minus p plus p cubed. This is a cubic. How many roots does a cubic have? How many roots does a cubic have? 3. The proof of that is the fundamental theorem of algebra. The best proof of the fundamental theorem of algebra that I know uses complex analysis. It uses those integrals I was just showing you. And you can prove the fundamental theorem of algebra that way. There's 3 roots. So we've got 1, 1/2, and 0. So then my question to you is the following. So class is ending. Imagine we now have a 5-game series. What p's are there such that the probability you win the first game is the same as the probability you win a series? 0, 1, and 1/2 still work. Are there any other real values of p that work? What if we have a 7-game series, a 9-game series? Is it just those 3 numbers? Or if we go up to 5, what do you think? Do you think there should be something else? What kind of polynomial will you have if you use a 5-game series? It'll be a degree 5. So a degree 5 polynomial has 5 roots, but the roots might not all be real. What might some of the roots be? They might be complex. And if your polynomial has real coefficients, the complex roots occur in complex conjugate pairs. This is why I was saving this for today, so that if I had a little extra time at the end, this ties in with our complex analysis stuff. When you're trying to analyze this problem, it will come back to potentially, do you have complex roots? It's not just space filling. Okay?